Okay, in example 3 here, we're looking to decide which of these slope fields represents the differential equation for dy dx equals cosine of x. And so if we think about this, there are a lot of different ways that we could make this determination. Probably the easiest, if we think about what cosine of x is when x is 0, let's go, dy dx is going to be the same for all values of y, and if we look at all these slope fields, it looks like dy dx is the same for all values of y at a given value of x. So then we think about, well, where do we know the value of cosine of x? And we know when x is 0, cosine of x is 1. And so we're looking for a slope field where the slope lines along the vertical axis are 1. And the only one that matches that characteristic is c. So I'm going to choose c. If you notice this row of slope lines here along the axis all have a slope value of 1, which that's not true about the slope lines in any of these other graphs. And so that's how I would have determined that that was the slope field for dy dx equals cosine of x. Alright, let's go to example 4. We're supposed to consider the differential equation x squared over dy dx equals x squared over y and sketch the slope field. So a few things here. First of all, we're going to have some values where for the slope field where it's undefined whenever y is equal to 0. So we're undefined at the horizontal axis. So whatever the case may be, our slope field is not going to, pardon me, I just had a moment there. Whatever the case may be, we can put vertical lines there in the slope field to represent the undefined slope, or we can leave slope lines out. I generally prefer to put undefined slope lines in there. So I'm going to go ahead and do that. Wherever y is 0, I'm going to have these vertical slope lines. If my pen will work. Hold on. I think I found a dead spot there. And I'm going to continue building the rest of my slope lines here. When y is 1, the value for the slope line is just going to be x squared. So when x is 0, actually all these other values where x is 0, maybe 0, and x is 1, we have a slope of 1, and when x is 2, we have a slope of 4, and a slope of 9. And on this side, a slope of 1, and a slope of 4, and a slope of 9. And down below the axis, when y is negative 1, we'll have x squared divided by negative 1, so the slope's going to be negative 1, and negative 4, and negative 9. And over here, we have negative 1, and negative 4, and negative 9. And up above, the slopes will flatten out a little bit. So let's see. When x is 1 and y is 2, the slope will be, or pardon me, when x is 1 and y is negative 2, the slope will be negative 1 half. And then negative 4 halves, or negative 2, and then negative 9 halves. Same thing on this side, negative 1 half, negative 2, negative 9 halves. And up above, when x is 1 and y is 2, the slope will be positive 1 half, and then positive 2, positive 9 halves, and positive 1 half, and positive 2, positive 9 halves. And then we're supposed to sketch the solution curve with initial condition f of 1 equals negative 1. So I'm going to plot point 1, negative 1. And as the slope comes out here, it steepens up. Oops, maybe something like this. And as we move towards the horizontal axis, it starts to flatten out. And I think our solution curve should look something like this. Again, anytime we make a solution curve, it's kind of an estimation. Alright, now, let's move on to part B. We're supposed to find the particular solution to the differential equation with this initial condition and then use it to find f of 2. So to find the particular solution, we take the differential equation, and now here we're going to use separation in order to integrate this. So I'm going to separate my variables, using y dy equals x squared dx. And then I integrate. And so I've got y squared over 2 equals x cubed over 3 plus a constant. We can solve this for y. Multiply both sides by 2. And then take the square root of both sides. Now, based on the initial condition, I can take this function and write it. Since y is -1 when x is 1, that means that we want the negative branch of this, because the y value is negative for our initial condition. And so we've got can't write a 3 here. I'll try this again. We've got y equals 2/3 x to the third plus c underneath that radical. And now I'm going to actually use the initial condition to find the value of c. So I'm going to have -1 is equal to the opposite of the square root of 2/3 plus c. And so we want what's inside the radical to be 1. So c is going to be 1/3. That gives us our specific solution, a particular solution to the differential equation, being y equals the opposite of the square root of 2/3 x to the third plus 1/3. And then we're asked to use that to find f of 2. So we're going to put 2 in here for x. We've got y equals the opposite of the square root of 2/3 times 2 cubed plus 1/3. And this ends up being, let's see, negative square root of 16/3, 17/3. Now, thinking about this for a second, that's what we get for our value of f of 2. If I take an approximation of that, the opposite of the square root of 17/3, we get negative 2.380. And so our value when x is 2 on our solution curve above should be about negative 2.38. And I missed it by a little bit. But it means that this curve should actually curve underneath this slope line right here. But we were pretty close. Alright. That's the end of that example.